Welcome to the online lecture 18 of Enumerative Combinatorics. And the topic today is something we have already implicitly done a little bit, and now we're going to do more of it. It's the topic of bijective proofs. So what is a bijective proof? Well, it's a proof using the bijection principle. So the fact that if there is a bijection from x to y, then the sizes are equal. So this principle can be used to prove lots of combinatorial identities, in particular binomial ones. Basically, whenever you have an identity where each side is the size of a set, you might ask yourself, could this actually follow from a bijection between the sets? And often enough, the answer is yes. Not always, but often. And sometimes these proofs are the easiest available proofs. So here is one very simple example before we get to something deeper. The symmetry of Pascal's triangle. Well, let me recall what it says. This was lecture 6, theorem 135. It's saying that for any n in n and k in R, we have n choose k equals n choose n minus k. Yeah, let me define n and k. Okay, how do we prove this? Well, we already know how to prove this. That was one of the easier proofs in the section, but let's prove this again. By the combinatorial interpretation of binomial coefficients, we know that n choose k is the number of k element subsets of the set n. Remember, this is the set 1, 2, n. And similarly, the same is true for the other side, except it's now n minus k element subsets. So now we are looking for a bijection from the set of all k element subsets of n to the set of all n minus k element subsets of n. Because once we have such a bijection, these two sets will be equal, so there will be a bijection between these two sets, so their sizes will be equal. But the size of this here is n choose k, and the size of this here is n choose n minus k, so these two things will be equal and will be done. Yeah, let me just spell this out, from this to this. Okay, so how do you find such a bijection? How do you transform a k element subset to an n minus k element subset? Well, you can complement it. You can take its complement. So such a bijection is here to here. S goes to n without s. Why is this a bijection? Well, you can, first of all, it's well defined because the size of the complement of S is n minus the size of S, which is k. So it is n minus k element. It's still a subset of n, clearly. This map, and furthermore, this map is invertible because to invert it, you just take the complement again. So the inverse of this, so first of all, this is a well-defined map. Moreover, it has an inverse map, which also sends each S to the complement, because the complement of the complement is again the original set. So thus it is a bijection. And hence the bijection principle yields the size of this here equals the size of the other one, which means that the number of the k element subsets is the number of n minus k element subsets. And as we know from the above, this is n choose k equals n choose n minus k. So the symmetry is again proved. And by the way, this perfectly holds even if k is like negative or irrational, then you're just proving 0 equals 0, but that's still, the proof is still true. I should remark one more thing, perhaps. You might also think of this as a proof by double counting, because basically here you're counting the k element subsets by choosing the elements that go into the subset. And here you can say you're counting the k element subsets by choosing the elements that don't go into the subset. And that's a valid way to think about it, but it's of course the same proof. Generally, there is a fairly fluid boundary between bijective proofs and proofs by double counting. The point is always to interpret the left and the right-hand side as counting something, and to show that they're counting more or less the same thing. And in this case, more or less means these two sets are in bijection.